Hello and welcome to part 3 of this week's lecture on open channel flows. In this part, we are going to look at some of the governing equations for the analysis of open channel flows. Okay. Just a reminder what we discussed in part 2 as well. So, what are steady state and uniform flows? So, steady state flow is a flow in which the properties are independent of time. And then you have the uniform flow in which the properties are independent of the length of the channel. Okay. And what it means that you have, for example, a velocity profile, it does not change along the length of the channel. Okay. But you might be in a situation where the velocity is not changing along the length of the channel, but it can change radially. Okay. So this is, for example, an open channel flow inside a pipe, and the velocity at the surface of the channel or at the wall is quite low because of the friction. But as you move towards the center of the channel, your velocity increases, and it will be maximum at the center, just like the case we discussed in pipe flow. Okay. And then you can have prismatic and non-prismatic channels. So prismatic channels are made by people, and the non-prismatic channels are mostly natural channels. Okay. And the properties of prismatic channels are that they are constant in cross-sectional area. They have a constant surface roughness because these are made by men. So they are made of certain materials. So that's why their surface roughness is constant. And these channels also have a constant slope. Okay. So because these open flow channels, the main driving force is gravity. So all these channels are always at a certain slope for the flow to happen, okay, due to gravity effect. And the slope of these prismatic channels are constant, okay. So they have a certain angle, and these are constant angles. Now, if you want to develop a relationship for a steady uniform flow, and what it means that the velocity is not changing, and if the velocity is not changing, it means that the sum of all the forces on the fluid element is zero. Okay. Or in other sense, that the different acting forces are equal in magnitude. So we have, if you, for example, look at this figure here, so you have this a rectangular channel, and we are looking it from the side. So for example, you have this is the front cross section, and you are looking at the side of this channel. Okay, so that is this side here. And if you look at it, we have two kinds of forces. You have gravitational force that wants the fluid to move downwards and want to give it speed. And then you have the drag force, the friction force, that want to slow down the fluid. Okay. And for this fluid element in the channel, we have the weight of the fluid that is acting downwards in the negative y direction. And if you resolve this component of W in the flow direction, that will be W sine alpha. And sine alpha, or alpha, is the angle of the slope. Okay, so the slope of the bed of the channel. And this fluid element has a length that is L, and the height of the channel from point 1 to point 2, for example, the height change is HL. Okay. So if the fluid is flowing, let's say from left to right, we can do a force balance and calculate what is the speed of the fluid. Okay. So if we do the force balance, we have the gravitational forces equal to drag forces. So gravitational forces is the force due to the weight of the fluid, that is W sine alpha, and the drag force is the shear force due to the fluid times the wetted area. Okay, and this toe node is the shear stress, so that is why we have to multiply it with the area to convert this whole thing into a force balance. Okay, so we have the W is equal to mg, and we can write the m as in the form of volumes times density times the gravity. So that is the W here. And for the case of sine alpha, from trigonometry, we know that if the alpha value is quite small, that is mostly the case for open channels, we can write sine alpha as the slope of the bed. Okay, so the slope of the bed would be the vertical distance divided by the horizontal distance. Okay, so the vertical distance from point 1 to point 2 is HL, and the horizontal distance is L. So the slope of the bed would be HL over capital L. Okay. And for the case of wetted area, we can calculate is as the length of the fluid element times the perimeter, that is the length of this channel that is in contact with the fluid. If you put these values into this equation here, we get the final equation that is equal to A times rho G HL over L is equal to tau naught P. And we can further write this equation in the form of hydraulic radius as we define in part 2, because that is one of the fundamental parameters of open channel flow. So we can write A over P as RH, and then we have the remaining term of rho GS. Okay. Now we have this equation of shear stress, but we don't know what is the value of tau naught. So what we can do, or what Chazzy, for example, suggested in 1700s, that we can use this equation through friction factors. So we can relate tau with the friction factor, that is the fanning friction factor. This is the same equation that you studied in chapter 6 when you were talking about friction factors. So we can write tau naught as a function of friction factor times the density of the fluid times the mean velocity. Okay, so if you replace tau naught with this equation here, you can write the final expression of velocity of the fluid in the open channel as U is equal to square root of 2 over F RHGS. Okay, so that is the velocity of the fluid in your open channel. We can simplify it further. We can write U by taking out these constant terms out, that is 2G over F, and we can write it as a constant C that is called as Chazzy coefficient, that has the units of meter half per second. And we can write the final equation of U as U is equal to C times RHS. Okay. And please remember that for the definition of C, we are using here fanning friction factor. Okay, we are not using Darcy friction factor that is represented by lambda, but in some notes you might see lambda as well. So if you are replacing C with the Darcy friction factor, then you have to use this equation here, not this equation. Okay, so please keep that in mind if you are using fanning friction factor or if you are using Darcy friction factor. Now, one problem with C, that is the Chazzy coefficient, is that is a function of Reynolds number, and as you know that Reynolds number is a function of U itself. So it means to know the value of C, you need to know the value of U first. Okay, so that is a bit tricky because we want to calculate the value of U, but to calculate the value of U, we need to know the value of U. Okay, so that is a bit tricky situation. So what we do, we try to use F. That is, for example, if you are in a laminar flow, we try to use F through first principles. And if you remember chapter 5, that friction factor was a function of Reynolds number, and we can write it in this form. And if it was a fully developed laminar flow, K was a value of 16. So we can calculate value of F just by F is equal to 16 over Reynolds number. Okay, so that gives you the value of F, and then you can just put into this equation and calculate the velocity of the fluid. This is much easier if you are in laminar flow. Unfortunately, in most of the open channel flows, the flows are in turbulent flow. It means that you have to use more complicated equations. For example, you have to use Coolbrook coefficient, or you have to use Haaland coefficient that you should have seen also in chapter 6 to calculate the value of f. But all these equations have limitations in the sense that they are applicable only to a certain value of Reynolds number, and also it is very difficult to find the value or absolute value of these surface reference coefficients. Okay, and so we mostly use Moody's chart to calculate the value of C. So by using Reynolds number, we go and look the value of F, that is the Fenwick friction factor, and by using Fenwick friction factor, we can calculate the value of C. Okay, so this is one of the ways we can calculate the velocity of the fluid in an open channel flow. But again, this is still complicated. So in 1800s, Manning, that is, who was an Irish engineer, he actually came up with a simplification of Manning's equation, and he said that we can write C as this, for example, that it is a function of 1 over n, that is the Manning's coefficient times hydraulic radius raised to the power 1 by 6. And this is a purely empirical equation. This is not from first principles. He just experimentally observed a range of different channel shapes and roughnesses, and then he came up with this equation using empirical analysis. Okay, so if you use this value of C in your equation of Chassis, we can write the final velocity profile or velocity equation as U is equal to 1 over n RH raised to the power 2 by 3 times the slope of the channel or the slope of the bed raised to the power half. Okay, so this is the equation that gives you the velocity of the fluid in the channel. Now for the value of n, that is the Manning friction factor, these values are available in handbooks or in the form of tables. And if you get a question, for example, related with open channel flows, you will be given either these tables where you have to select the value of n for a certain material, or you will be given the value of n directly into the question. Okay, so you don't need to memorize these values. So we know the value of C, that is the Chassis coefficient or the Manning coefficient. Through Manning coefficient, we can calculate the value of U. But as chemical engineers, we always want to calculate the flow rate. So we can calculate the flow rate by multiplying velocity with the area. Okay, so if you multiply this U with A, we get the flow rate of the system. Okay, so that is relatively simple equation. You just need to know the value of n. You calculate the value of A and RH and S, and you know the value of Q. Okay. This Manning, if you look at this equation here, that is I circled, the Manning's equation is actually not homogeneous, not dimensionally homogeneous. It means that n is not a unitless or a dimensionless number. It has a unit. Okay. But for example, in this table, as you can see, that it looks like that it is dimensionless, but actually it has dimensions of t, that is time over length raised to the power 1 by 3. Okay, but despite its non-homogeneity, this equation is still popular because it is a very simple equation to give you the simple analysis of open channel flow. Okay, so that was for the case of open channel flow, but you can have situations where within a large channel you can have small composite sections. Okay, so what it means that you can have, for example, in this large channel, you can have sections with different Manning coefficient or different friction, surface frictions. It means that you have to now calculate the effect of all these different sections in the total flow rate through this channel. Okay, so how we can do that? To do that, we have to calculate an equivalent Manning coefficient. Okay, so the rest of the equation is the same. The only thing that is different is we have to calculate an equivalent Manning Manning coefficient for the whole channel that should account for the individual Manning friction coefficients, and at the same time, each of the subsections will have a different parameter as well. Okay, so if you do that by using this equation, you can calculate the flow rate through this composite section channel. You can also have a situation where actually you have a compound channel. So what is a compound channel? So a compound channel is a channel for which the cross section is composed of several distinct subsections, as it is shown here. Okay, so for example, you have this large channel, but inside this large channel you have actually distinguishable subchannels. Okay, so how to solve for this compound channel? So first you have to divide this large channel into multiple subchannels. For example, here I have divided into subchannel 1, subchannel 2, and subchannel 3. And then you calculate the flow rate from each of these subchannels. Okay, so each of these subchannel will give you an individual flow rate by using this equation here. And to calculate the flow rate, you have to calculate the individual cross-sectional area. You have to use the individual Manning coefficient, sorry, and you have to use the parameter of each of these subsections. And by doing that, you will get a flow rate from each of these subsections. And then to calculate the total flow rate, you sum up all the flow rates for each of these subsections to get the total flow rate. Okay. And we will do few exercise questions on this concept in the tutorial. And I hope that will help you there, that how we can actually use the concept of compound channels to calculate the flow rate. Another thing that is just a reminder of, for example, of Bernoulli's equation, but now we are looking at how we can apply it to open channel flows. So similar to pipe flow, we have three kinds of energy. We have the elevation head, we have the pressure head, and we have the kinetic head. And if you apply that, for example, this energy equation on the open channel flow, so you can see that this red line is the energy gradient line. It means that it accounts for these three types of energies. And then you have the what we call it hydraulic gradient line, and hydraulic gradient line is actually the sum of z plus y. Okay, so it is the elevation head plus the pressure head. Okay, or you can say that hydraulic gradient line, you can get it by subtracting the kinetic head from the total energy head or the energy gradient line. Okay, and if you notice here that for the case of open channel flow, the height of hydraulic gradient line is the same as the surface of the bed, okay, or the surface of the fluid. So how we can use the equations that we developed for pipe flow for open channel flow? So just have a look at it. So for the case of like an open channel flow, again, if you look at this system here, so you have an open channel flow. You have a bed slope of S node that is constant. It means that you are in a uniform open channel flow. And you have the flow direction that is in X direction, and you have the slope of the bed that is alpha. Okay. You have, for example, velocity V1 and V2 going from section 1 and section 2. Now, if you try to apply the continuity equation, so you can see that for a steady state uniform open channel flow, you can just use the same continuity equation that you use for pipe flow. That is V1 is equal to, V1A1 is equal to V2A2. Okay. For the case of Bernoulli's equation, there is a slight difference. So for the case of Bernoulli's equation, you have this relation here. You have the elevation head plus the pressure head plus the velocity gradient or the kinetic head. And this kinetic head is now multiplied with a correction factor that is alpha. And the reason we have multiplied it with alpha, because to correct for the change in velocity, because now the the mean squared velocity is not equal to the square of the mean velocity. Okay, so it means that we have to correct for the non-uniformity in velocity in the open channel. And similarly, we have alpha 2 on the other side. And we have another parameter that is HL that you studied, that is the head loss when you are going from point 1 to point 2. So some of the energy you are going to lose in friction, and that is accounted by using this term HL. Okay. Now this HL can be written as SF times delta x, and SF is the slope of the this fluid. Okay, so how the fluid is changing from point 1 to point 2, and if you multiply it with the delta x, that is the length travel, okay, of the fluid from point 1 to point 2, so you have HL, that is the head loss, is equal to the the vertical distance traveled from point 1 to point 2 divided by the horizontal distance traveled from point 1 to point 2. Okay, and we can also write the slope of the channel itself by using this term here. So we can simplify this equation here, that is z1 minus z2. Again, that is the vertical distance traveled from point 1 to point 2 divided by the delta x, that is the horizontal distance travel. Okay, so just to clarify that S node is the slope of the bed, okay, this slope here of this bed, while SF is the slope of the liquid surface. Okay, so that is sorry, where is the arrow? Yeah, so that is the slope of this liquid here. Okay, and if you are in a uniform steady state flow, SF should be equal to S0. Okay, it means that you have negligible head loss. Okay, and as such we can actually cancel out this part of this equation here. But if you don't have a uniform flow, and if you have two different slopes of the fluid and of the bed, then you have to account for this equation here for the head loss. Okay, so Bernoulli's equation can be modified slightly to be applied on the open channel flow. So some of the key concepts that we discussed in this lecture. So when we are talking about open channel flow, we have a free surface. We have different types of channels. We can have natural or artificial channels, but they are always driven by gravity. There is no pressure gradient. We discussed that we can have different types of flows. We can have laminar, turbulent, steady, unsteady, uniform, and varied flows. Okay. Channels can be prismatic or they can be non-prismatic channels depending on the shape and the roughness. If there is a constant velocity in a uniform flow, it means that the gravitational force and the drag force balance out to give us the uniform velocity. We define the parameter RH, that is the characteristic parameter for open channel flow, that is A over P. And we also saw that for the case of open channel flows, the Reynolds number should be around 500 for a transition from laminar to turbulent flow. Then we developed the Chassis equation to calculate the velocity of the fluid in the open channel, and we saw different simplifications of C, that is the Chassis coefficient, and the most useful simplification is by Manning, and Manning actually make this equation quite simple by using just one coefficient, that is N, that is Manning friction factor, that you can get experimentally. Okay, and that is the final equation for the velocity of the fluid in the open channel flow. Okay, so that is all for this part. Thank you for your time.